In this lecture, we would discuss the continuous time unit step function. We would also see the relation of unit step and unit impulse function, as we have discussed unit impulse in our previous video. A continuous time unit step function, which is denoted by u of t, it is defined mathematically as equal to 0. This function is equal to 0 when time is less than 0, and it is actually equal to 1 when time is greater than 0. So if we want to plot this function graphically, we can plot it easily on time axis. We have a time axis, and suppose this is 0 instant, right? This is 0 instant, and we say we are interested in plotting u of t. So it has 0 value when time is less than 0, and it has a value 1 when time is greater than 0, right? So for all this instance where you have positive time, it has a value unity 1. It is 1, right? Now it means there is a jump here from 0 to 1 at 0 instant. So you have a signal which has 0 duration and it approaches unity, right? This the peak is unity. So if we can, so it means we can also write our function u of t in terms of the delta function, the unit impulse function, right? The unit impulse function, and that is, we can say delta of tau d tau. It's basically an integral of minus infinity to t. Let me explain this notation, because sometimes students are confused with this one. That's how we represent it with this as this integral unit step function. So let me explain this idea. Now if you concentrate on the unit impulse, as we have defined the unit impulse as we graphically represent the unit impulse in this way, that we have a signal at 0 instant, and the area of this signal, this pulse, a pulse with a very short duration, such as 0, and the area is unity. Now if you integrate this unit delta of t, right? If you integrate it, suppose you are integrating this delta of t or delta of tau, you can say. Let me change it to tau instead of t, so that we are consistent with our notation. Suppose instead of t we are using tau variable for time, to represent time. So delta of tau is 0. At 0 it occurs, and it has some value here at 0. Now if we integrate this delta of tau from somewhere from minus infinity up to this end, just when suppose we say our time is negative, right? It has some negative value. So in this range, this function has no value delta of tau, right? It has no value here from minus infinity up to this 0, just before 0. It has no value. So if we solve this integral from minus infinity up to some point which is just before, if t is negative, right? For some negative value of t less than 0, some less than 0 value of t, if we integrate it, right? If we integrate it for t, and suppose that t is negative, so what would we get? We would get no value. We would get delta of this integral, delta of tau d tau would be 0. So if we plot this one, u of t, which is an integral for any negative value of t. If we take any negative, -1, -2, minus 0.5, whatever is the value of this variable t, if we integrate it, you would get 0. So if we plot the value of integral, if we plot this, suppose we take t equal to -2, right? Suppose -2, if is this t is equal to -2, so the integral would have a value 0. I will plot 0 here. So if I have t equal to -1, again this integral t equal to -1, this integral would have 0 value. I will plot it here. T equal to minus 0.5, right? 0.5, 0 value, and so on. But as soon as this t becomes a smaller positive, if suppose this t has some value over here, some positive value, some value greater than 0, right? Some value greater than 0, any smaller positive value, maybe 0.001, whatever it is, if it has some value greater than 0, now the integral at instant 0 or some very small value, 0.0001, suppose it passes this 0 point. If this is the some positive value, right, then this integral would have a value 1. So for that instant, which is very close to 0, it would have a value 1, because the integral is integrating an impulse and the area of the impulse is unity. So I get this point at 0. Similarly at 0.5, I would get the same point 1, the same integral 1. For t equal to 1, I'll get again 1. T equal to another positive value 1. And if you join all these points, you get, basically you get the u of t. For continuous values of t, if you take these values, these are actually the unit step function. You get the unit step function. So basically you can represent your unit step function. You can represent your unit step function u of t as an integral of delta of tau d tau from -infinity to t, right? So this function is basically, this is how you say that this is our definition. Now if this is the integral of delta of tau, right? So now you should be clear about the representing the unit impulse. You can also represent the unit impulse in terms of the unit step function, right? So we can easily say, just from our mathematics, that we can say that our delta of t is basically the derivative of the unit. It is the derivative of the unit step function. We can write the unit impulse function. We can write the unit impulse function. We can define it at 0 for t greater than 0 and t less than 0. Sorry, it should be t less than 0, and it is unity for t greater than 0. Or we can rewrite it mathematically in terms of the impulse function. Let me change this variable to be correct. Let me change this variable. This is tau d tau, because we are using t here in the limits, right? So we change this variable to tau. You can write the unit impulse unit step function in terms of the unit impulse function, right? And you can similarly write, if it is the integral, so delta of t would be the derivative of the unit step function. This is the conclusion of this is the summary of this lecture on the unit step function.